Welcome to the course on power quality. We are discussing the hybrid power filters. So, we are taking numerical examples. So, starting fifth numerical example, a single phase universal active power conditioner consisting of shunt and series active power filters using 2 voltage source converter with common DC bus as shown in figure is designed for a critical load of 230 volt 50 hertz single phase resistive load of 20 ohm through a phase control AC voltage controller at a firing angle of 30 degree of its thyristor, and if there is any if there is a voltage fluctuations of plus 10% minus 20% in the supply voltage with the base value of 230 volt, calculate A the voltage rating of shunt element, B current rating of shunt element, C VA rating of shunt element, D voltage rating of the series element, E current rating of series element, F VA rating of series element of the universal active power conditioner to provide harmonics and reactive power compensation for unity power factor at AC means with constant sine wave voltage of 230 volt across the load. So, this is the typical load. We have a AC voltage controller with the resistive load and we have here the supply. So, we are connecting a series this universal active power filter where we have a series element to inject the voltage because there is a voltage sag and swell, and we are connecting this shunt compensator active filter across the load which takes care of current harmonic currents and reactive power of the load. And after making the model of this whole system and simulating it with the data given in the column, so waveforms are plotted here. So, this is supply voltage, this is supply current after the compensation, this is the load voltage and this is the load current typically drawn by this AC voltage controller, and this is the shunt active filter current, and this is the typically the voltage injected by series active power filter because it is only the voltage sag and swell. So, that had to inject the voltage like. So, coming to the solution part of numerical part of the solution. So, given that supply voltage of 230 volt 50 hertz, 230 volt RMS 50 hertz a non-linear load of phase control AC voltage controller consisting of 2 resistance of 20 ohm and firing angle of 30 degree. There is a voltage fluctuations of plus 10% minus 20% in the supply voltage with the base value of 230 volt. A single phase universal active power conditioner is used to provide the power factor at the AC means and constant sine voltage of 230 volt 50 hertz across the let X be the per unit voltage variation in Vs to at the PCC under voltage variation. So, in this system the load current harmonics and reactive power compensation are to be provided by the shunt active power filter of the universal active power conditioner, and the voltage sag swell compensation provided by series active power filter of universal power conditioner. However, while compensating for voltage sag and swell, an active power is circulated between the series and shunt active filter as explained in earlier, and using the voltage dip, maximum voltage dip, the maximum rating of the series of the two VSC are realized. So, various rating the various rating calculations are as follows. So, the supply voltage under the maximum voltage sag is typically X is here 0.8. So, the voltage reduces to 184, and a single phase control AC controller, the waveform of supply current has a value of Vs upon R from alpha to pi. So, the typically the voltage of supply under nominal condition is 230 volt. So, peak is 230 into root 2, that is 325.27 volt, and the load RMS current from this relation IL equal to from this relation of AC voltage control it comes 11.33 ampere, and the fundamental RMS current typically from in AC voltage control relation comes from at given firing angle plus resistive load and voltage it comes 11.206 ampere, and the angle between the fundamental voltage and current theta 1 calculated in terms of alpha it comes 4.684. So, RMS active power component of load current IL1 cos theta 1 comes 11.169 ampere. So, the active power consumed by the load is the voltage and active load voltage, that is 230 volt multiplied the active component of current. So, it comes 2568.771 watt, and the supply current under maximum voltage variation minus 20% sag. So, we can PL that active power divided by the voltage minimum voltage on supply. So, it is a 13.96 1 ampere, and the total harmonics and reactive power component of load current is calculated from RMS current multiplied fundamental active component current square. So, putting the value it comes 1.912 ampere, and the voltage rating of the shunt element of universal active power filter is equal to the AC voltage of 230 volt, since it is connected across the load of 230 volt sine waveform. The current rating of shunt element of universal active power filter is computed as the shunt element of universal active power filter is to provide the load current harmonics and reactive power compensation. Hence, the required harmonic current and reactive power of the load and it has to supply. Therefore, the total harmonics and reactive component of load current to be supplied by the shunt element, that is I shunt R equal to ILR, that is 1.921 ampere, and the supply fundamental voltage is lower than the compared to the required voltage. Hence, the shunt active power filter absorb the active power, that active power is delivered back to the system via series active power filter. So, shunt active component of the shunt active power filter current is estimated as I shunt IS minus ILA. So, putting the value it comes 2.792 ampere, and the overall current rating of shunt active filter is now RMS value of the your active component current and then the harmonics and reactive component, putting the value it comes 3.389 ampere, and the V rating of shunt active filter will be VSH ISH. So, VSH is 230 volt because it is connected across the directly the typically across the load where the nominal voltage of 230 volt is there and current is 3.389 ampere. So, it comes 779.476 VA, and the voltage rating of series element is computed as there is a voltage fluctuations of 10% plus 10% minus 20% in supply system with a base value of 230 volt. Therefore, the series active filter must inject the difference of the maximum these two voltage to regulate the voltage at the load terminals. The voltage rating of the series active filter is 230 into the sag of 20%, that is a 46 volt, and the current rating of series active filter is same as the supply current under voltage sag. So, we calculated already, that is typically the supply current under voltage sag, that is 13.961 ampere. So, VA rating of the series element is your voltage across the series, that is 46 volt, and current through it, it comes 642.206 VA. Coming to the sixth numerical problem, a single phase voltage source inverter with a quasi square waveform AC output of 230 volt 50 hertz is feeding the critical load of 230 volt 50 hertz single phase thyristor bridge with a constant DC current of 30 ampere at the 60 degree fire angle of thyristor, and single phase universal active power conditioner is designed for this critical nonlinear load. Calculate a voltage rating of shunt element, current rating of shunt element, VA rating of shunt element, and the voltage rating of series element, and the current rating of series element, and the VA rating of series element of universal active power conditioner to provide harmonics and reactive power compensation for unity power factor at AC means pi shunt element of universal active power filter, and constant regulated sine wave voltage of the 230 volt RMS sine wave at 50 hertz across the load by series element of universal active power filter. So, this is the typical circuit. I mean, we have here the voltage given by like a kind of quasi square wave, and we have a AC voltage controller, the load thyristor converter with the, and we want constant sinusoidal voltage across it. Like, so, the voltage typically what we are getting here, we are getting typically of this nature from the inverter at the input of the system, and then we have a typically source current we want sinusoidal and in phase with the this voltage, and the load voltage again we want sinusoidal. So, the difference of these two we have to inject by series filter, and the load current is here the constant typically square wave current because of thyristor converter with constant current, and the difference of the two this current supply current and the load current is supplied by shunt active filter, which consists of harmonics as well as the reactive power component of current. Like, so, after realizing this complete system, developing a model and putting the realistic value of which is given in the problem, these waveform are achieved, and now based on this we can go to numerical part of the problem. So, given that the supply voltage of 230 volt 50 hertz, RMS quasi square wave frequency of 50 hertz, a critical load of 230 volt 50 hertz single phase thyristor bridge with a constant DC current of 30 ampere at 60 degree fire angle of its thyristor, and in this system load reactive power and harmonics current composition are to be provided by the shunt active power filter of universal active power conditioner. The voltage compensation is provided by series active filter, and however, there is a difference in the magnitude of the fundamental voltage in the supply and the load terminal. To compensate that, an active power is circulated between the series and shunt active filter as explained in earlier. The rating calculation for both VSC and voltage source converter of universal active power conditioner are as follows. So, load current is a kind of you can call it square wave current with the amplitude of DC link current. So, the load RMS current will be of same as being a square wave, that is 30 ampere, and the fundamental current is estimated from that, that is 0.9 to 2 root 2 upon pi, that is 0.9 into IDC, and the fundamental active component of current will be your IL1 into cos alpha. So, putting the value, it comes 13.5 ampere, and the harmonics and reactive power component of load current is estimated from RMS current square minus the fundamental active component square. So, it comes like putting a value 26.71 ampere, and amplitude the C square wave is estimated for the input supply voltage. So, that comes typically your 281.69 from 230 volt RMS, and the fundamental component of this supply voltage will be in terms of now DC, it is a typically 219.634 volt, and the active power consumed by the load will be now your load voltage 230 volt and active component comes 13.5 ampere. So, this is 3105 watt, and the supply current is estimated now PL upon VS1. So, that is 3105 divided by 219.63, that comes 14.137 ampere. So, the voltage rating of the shunt element of universal active power conditioner is equal to the load voltage of 230 volt, since it is connected in across the load of 230 volt sine waveform, and the current rating of shunt element of universal active power filter is computed as follows. The shunt element of the universal active power is to supply load current harmonics and reactive power compensation, as the total harmonics and reactive power component of load current through shunt active filter is ISH are equal to IL square minus the fundamental active component of current square, and root of that putting the value, it comes 26.791 ampere, and supply fundamental voltage is lower as compared to the required load voltage. Hence, the shunt active filter absorb the active power, and that active power is delivered back to the system via series active power filter, and the active power component of the shunt active filter is estimated as IS minus IL1A. So, putting the value, it comes 0.637 ampere, and the net current rating of shunt active filter is active component of current square plus reactive component current square the harmonics, and under root of that putting the value, it comes 26.799 ampere, and VA rating of shunt active power filter is now voltage and current rating of it. So, voltage nominal voltage, which is because it is connected across the load of 230 volt, and current rating is 26.799 ampere. So, it comes 6163.674 volt ampere, and the voltage rating of series element of universal active power conditioner is estimated as follows. The supply voltage is C square wave of 230 volt RMS, and the load voltage must be sine wave of 230 volt RMS. Therefore, the series active filter must inject the difference of these two voltage to provide the required voltage at load end, and this is the voltage rating is calculated from, because for first 30 degree there is no voltage from the inverter. So, this is from the voltage from the load side, and this is typically from inverter side minus the load side, and this is on load side. So, after estimating RMS, this comes 69.05 volt, and current rating of series element is the same as the your supply current. So, that is IS equal to 14.137 ampere, and the V rating of series element is your series injected voltage multiplied the current. So, injected voltage we calculated 69.05 multiplied the current 14.137. So, it comes 976.176 VA. So, coming to 7th numerical problem, a single phase voltage source inverter with a square wave AC output of 230 volt at 50 hertz is feeding the critical load of 220 volt 50 hertz as single phase, and consisting of uncontrolled diode bridge converter having a RA resistive and band EMF load with resistance equal to 4 ohm and E equal to 216 volt. A single phase universal active power conditioner consists of shunt and series active power filter using a 2 voltage source converter. A common DC phase capacitor is used, and which is designed for critical non-linear load. Calculate the A voltage rating of the shunt element of universal active power filter, B current rating of the shunt element of universal active power conditioner, C the VA rating of the shunt element of universal active power filter, D the voltage rating of series element of universal active power filter, and E the current rating of series element of universal active power conditioner, and F the V rating of series element of universal active power conditioner to provide harmonic and reactive power compensation for unity power factor AC mains by shunt element of universal active power filter, and constant regulated sine voltage of 220 volt RMS sine wave at 50 hertz across the load by the series element of universal active power conditioner. So, these are typical circuit that this here we are getting a square wave, and then we want sine wave across this, and this is the load which we call it voltage fed load, typically used to charge the battery, and we have here the shunt element to take care of harmonic current and if there are any reactive power of the load, and here we have a square wave. So, we want sine wave voltage here. So, this series filter have to inject this. So, after developing the model if and putting the value which are given in the problem, these are the simulated result. So, supply voltage is like a square wave which is given by inverter, and we want supply current sinusoidal in phase with the voltage, and this is the load voltage which we want across the load sine wave. These are typically load current, which draws only current for very small duration when your battery voltage is, let us say supply voltage greater than the battery voltage, then only current flows only for a small portion, and the difference of this and this certainly provided by shunt active filter which takes care of harmonics and reactive power, and then this is the voltage which is difference of your sine wave and the load voltage that is injected by series element. So, these are the waveform of this circuit. So, based on this now we can go to the calculation part of the problem. So, given that the supply voltage of Vs equal to 230 volt RMS square wave, frequency of 50 hertz and a critical load of 220 volt 50 hertz single phase consisting of uncontrolled diode bridge converter which has a Re resistant back EMF load with R equal to 4 ohm and E equal to 216 volt, and in this system the load reactive power and harmonics current compensation are to be provided by shunt active power filter of the universal active power conditioner, and the voltage compensation is provided by the series filter of universal active power conditioner. However, there is a difference in magnitude of fundamental voltage in the supply and load terminals to compensate that an active power is circulated between the series and shunt active filter to, and the rating calculation for both of VSC of active universal active power conditioner are as follows. So, the amplitude of square wave is the same as typically your DC will be the input DC will be the same because it is a square wave as the, so it is a 230 volt, and the fundamental supply voltage will be your 2 root 2 by pi, that will be 0.9 into Vs DC. So, it comes like a 207 volt, and however, the load terminal voltage is needed to be regulated to 220 volt. So, under this reduced fundamental voltage, the rating calculation for both the conditioners are as follows. In single phase diode bridge converter with Re load, the current flows from angle alpha when the AC voltage equal to E and to the angle beta at which the AC voltage reduces to E. So, and the peak voltage of this is equal to RMS multiplied root 2 because it is a sine wave. So, it comes 311.13 volt, and the alpha from this if we calculate, so putting the value it comes 43.696, and beta at which the current quenches it comes 136 point, and the conduction period beta minus alpha is 92.06. So, it means the diode are conducting only 92.06 degree in place of your 180 degree. So, the RMS load current is the RMS of discontinuous current at the AC main, and where the you can calculate from this formula of alpha. So, IL comes 12.32 ampere RMS, and an average current flowing into the battery you can calculate it from this relation. So, it comes 8.02 ampere, and the active power drawn from the AC mains will be your loss in this resistance, and then the battery charging power. So, that is the loss in resistance and the battery charging power. So, it comes 2339.8 watt, and now the active power component of fundamental load current of AC mains will be PL upon VL. So, you have a power and you have a VL. So, it comes 10.63 ampere, and the supply current is estimated PL upon VS1. So, that is 2339.8 divided by 207 fundamental voltage across the load in the supply. So, it comes 11. Typically 30 ampere, and the harmonics and reactive power component of load current you can calculate from RMS current square minus the fundamental active component current square and root of that. So, putting the value here it comes 6.22 ampere, and the voltage rating of shunt element of U is equal to the your load voltage which is 220 sine wave across the load, and the current rating of shunt element is computed as follows. The shunt element of universal active power conditioner supply all current, harmonics and reactive power component of the load current. Hence, the harmonics and reactive power component of current from the shunt active filter is as follows: IR square my ln square. So, putting this 6.22 ampere, and the supply fundamental voltage lower as compared to required voltage. Hence, the shunt active filter absorb the active power, and that active power is delivered back to the system via series active filter. So, active power component of current from the shunt active power filter is estimated IS minus IS1. So, calculating from that it comes 0.67 ampere, and the current rating of shunt active filter is your active component square plus harmonics and reactive component square, and the root of that, putting the value, it comes 6.25 ampere, and the V rating of shunt active filter comes your voltage rating of shunt active filter multiplied the current, putting the value, it comes 1434.4 volt ampere. Now, the voltage rating of series element of universal active power filter is computed as the supply voltage is square wave of 230 volt RMS, and load voltage at load terminal must be sine wave of 220 volt. So, therefore, series active power filter must inject the difference of these two voltage to provide the required voltage at the load end, and this voltage of series injection have to be, we have a typically 230 RMS minus 230 DC square wave minus this sine wave of 220 RMS with a peak of root 2. So, it comes 100.93 volt, and the current rating of series element of universal active power conditioner is same as the supply current, and the current rating of this element is same, IS equal to IS E equal to 11.3, and the V rating of series element of universal active power conditioner will be VFSC into IS. So, the voltage we calculated already 100.93 multiply the current 11.30. So, it comes 1140.5 VA. So, coming to the numerical problem 8, a single phase active hybrid filter consisting of one branch passive shunt filter and a high pass damped filter and series active filter connected in series with the AC mains using voltage source converter with DC bus capacitor is designed for a load of 230 volt 50 Hz thyristor AC controller with a resistive load of 20 ohm at 60 degree fire angle of its thyristor. Calculate the rating of both the series active power filters and the elements of passive shunt filter used in hybrid filter to provide harmonic compensation and reactive power compensation for unity power factor at AC mains. So, this is the typical circuit. We have a supply here, and we have a typically series active filter, and we have a non-linear load with the AC voltage controller, resistive load with the back to back thyristor, and we are putting a passive filter here. The role of series active filter is to push the all harmonics current into the typically into passive filter, and the design of passive filter is done corresponding to that the entire reactive power required by the load should be provided by this, you can call it fundamental reactive power generated by shunt active power filter. So, after designing and developing the model of it and putting the value given in the problems, the waveforms are simulated, and these are here supply voltage, this supply current after the compensation, this is the load current of AC voltage controller here, and this is typically the difference of these two, which consist of reactive power as well as active power component flows into the shunt filter, and this is the voltage injected by your series filter in that case. So, it of course, it has a, you can call it like a your shunt filter takes care of reactive power and harmonics, but series filter forces this passive shunt filter to take care entire compensation of reactive power and harmonics. So, coming to your numerical portion part, given that supply RMS voltage of 230 volt, frequency of supply 50 Hz and resistance of 20 ohm and firing angle of AC voltage controller 60 degree, a single phase active power condition filter hybrid filter consisting of shunt passive filter and series active filter yielding voltage source converter with DC bus capacitor connected in series with the AC mains is designed for the load compensation, and in single phase control AC control, the waveform of the supply current has a value of Vs upon R from angle alpha to pi. So, peak load voltage will be 230 into root 2, that is 325.27, and the AC RMS load current you can calculate from this, typically from this relation. So, it comes 10.315 ampere, and the fundamental RMS current will be your again from this relation. So, it comes 9.65 ampere, and the displacement factor or power factor angle from this relation in terms of alpha, it comes 16.52 degree, and the fundamental active power drawn by the load will be your Vs IL1 cos theta 1. So, it comes putting the value of this 27.79 1 watt, and the reactive power drawn by the load will be V s I L 1 into sin theta 1. So, putting the value it comes 631.412. So, this reactive power is required to be compensated by passive filter. So, capacitor value from this we have to design correspond to that, and the load RMS voltage which is across the AC controller comes equal to that is 206.3 volt corresponding to that fire angle, and now displacement angle will be your cos theta 1. So, that is typically value. So, it comes 0.959, that is the corresponding to reactive power down, and the load distortion factor we can find out your fundamental current divided by load RMS current. So, putting the value it comes 0.936, and the power factor is your dPf multiplied dF. So, it comes putting value of both it comes 0.897, and the AC means current after the compensation is IL1 cos theta 1. So, PL1 Vs. So, this comes putting the value here. So, it comes 9.251 ampere, and the shunt passive filter has to meet the reactive power requirement of the load for unity power factor at the AC means. Therefore, the capacitor of passive shunt filter must be selected to provide this reactive power, and from this reactive power what we calculated by the load we can calculate the capacitor from this relation. So, it comes 37.993 microfarad. Since there is only one branch of passive shunt filter which must be tuned for the lowest harmonic, third harmonics, in this case present in the load current, a damped filter to take care of all the harmonics current. Therefore, this value of the capacitor is the element of this passive filter. So, only one is there. So, we can call it is a 37.993 microfarad, and value of the inductor from high pass damped filter which is tuned at third harmonics we can calculate. So, this comes 29.631 millihenry, and the resistance in parallel of the inductor of high pass damped filter is calculated R h equal to X h by QH. So, taking a typically here taking a value, calculating the value X h and putting the quality factor of phi, it comes 5.585 considering the quality factor of phi, and the lower losses within the range 0.5 depending upon the attenuation required, and all the harmonics of load current to flow through high pass damped filter. So, it is a IL1 minus IL1 square. So, that comes typically 3.644 ampere, and all higher order harmonics voltage at the load and across the passive filter is typically comes to be IH into RH. So, putting the value of this harmonics, so it comes 20.350 volt. This much the voltage your series active filter have to generate at the point of common coupling, so that all the harmonics are goes into the passive filter. So, all harmonic voltage other than fundamental voltage, the load voltage and across the passive filter is your VH into IH. So, this is 20.35, and the voltage rating of the passive filter will be your RMS voltage square plus all harmonic voltage square. So, it comes 230.855 volt, and the current rating of passive filter is IL square minus IS square. So, from this you can calculate 4.563, because not only takes harmonic current, but it also takes your reactive current. So, V rating of passive shunt filter VPF into IPF. So, voltage we already calculated 230.899 and current of it 4.563, it comes your 1053.523 VA, and the per unit rating of the passive filter is your passive filter rating divided by the VA rating of the load. So, from this putting the value it comes only 0.444. So, the shunt passive filter is require 44.407% of the load rating. The series active filter must inject this all harmonic voltage to force all harmonic current into the passive filter. Therefore, the voltage rating of series active power filter will be typically V equal to Vs. So, that is 20.35, and the current rating of the series active filter is the same as supply current fundamental active power component. So, that is calculating like P1 upon Vs. So, it comes 9251 ampere. So, since series active filter is connected series with the AC mains before the passive shunt filter, which is providing the harmonics and reactive power compensation in UPF at the AC mains. So, the V rating of series active filter voltage multiplied the current, it comes typically voltage is we calculated 20.350 multiplied 9.251. So, it comes 188.258 VA, and the per unit rating of series active filter is the V rating of series active filter divided by the load V rating. So, it comes 0.079. So, the series active filter rating is only 7.935% of the load rating. So, coming to the ninth numerical problem, a 3-phase voltage source inverter with Cauchy square wave AC output line voltage of 400 volt RMS at 50 Hz is feeding a critical load of 415 volt 50 Hz 3-phase 40 kVA 0.85 lagging power factor load. A 3-phase universal active power conditioner is designed for this critical non-linear load. Calculate the A voltage rating of the shunt element, current rating of shunt element, V rating of shunt element, and the voltage rating of series element, current rating of series element, and the V rating of series element of universal active power conditioner to provide harmonics and reactive power compensation for unity power factor at AC mains by shunt element of the universal active power conditioner and constant regulated sine wave voltage of 415 volt RMS at 50 Hz across the load by series element of universal active power conditioner. So, this is the typical circuit. We are getting a like kind of Cauchy square wave of this kind at the input of this or you can call it supply to feed this load, and we have a load here typically RL lagging power factor load. So, shunt filter is supposed to provide the reactive power here, series filter is supposed to provide sine wave, the difference of this Cauchy square wave and sine wave. So, after making the complete model of this system and putting the with the value of which are given in the problem, the whole model is simulated and the simulated performance is here. The input voltage, this is the supply current and this is the load voltage after the compensation, and this is the load current. So, it is a series. So, and then you can call it is a shunt filter current because that provides the reactive power, and this is the series voltage injection, the difference between the load voltage and this. So, based on this waveform, then coming to numerical part of the solution, given that the VSL is equal to 400 volt RMS Cauchy square wave of line voltage and frequency of 50 Hz and a critical load of 40 kVA for 15 volt 50 Hz and 0.8 lagging power factor, and the desired load phase voltage is 415 by root 3, that is 239.6 volt of sine wave, and the magnitude of DC side voltage of the VSI is estimated VSFL root 2 by 3. So, it comes typically 489.89, and the total line current, load line current will be your given VA divided by the typically the 3 into voltage across the load. So, it comes 55.648 ampere, and the active power component of load line current will be your VA into power active power divided by 3 into voltage. So, it comes typically 47.031 ampere, and the fundamental component of the supply side line voltage will be from Cauchy square wave for fundamental of it. So, it comes 381.972 volt, and the fundamental component phase voltage will be by root 3, so it is 220.532 volt, and rating calculation supply current after the compensation of course will be based on the voltage, this fundamental voltage and the power here. So, it comes 51.391 ampere, and the rating calculation for both VSC of as follows. So, voltage rating of the shunt element of is a AC load voltage, that is 239.6, since it is connected across the load of 239.6 volt sine wave form, and the current rating of shunt element of universal active power compensator is computed as follows. The shunt element of UKC compensate for load reactive power, and the required reactive power component from shunt filter is calculated here. So, we have RMS load current multiplied the fundamental active component of load current. So, putting the value here, it comes 29.315 ampere, and the active component of shunt active filter, which is circulating from shunt to series, it is your IS minus ILA. So, it comes 4.09 ampere, and the net current rating of shunt active filter is your active component of current square minus the typically your reactive power and harmonic current square under root of that. So, putting the value, it comes 29.599 ampere, and the V rating of shunt active filter will be 3 into VSH into ISH. So, putting the value, it comes 21.276 kVA. So, the supply of Cauchy square line voltage results in a step voltage. The waveform of the phase voltage of the input series voltage is step waveform. First step is pi by 3 angle from 0 to pi by 3 with the magnitude of VDC by 3. Second step of pi by 6 pi by 3 angle again pi by 2 to pi by 3 as a magnitude of 2 VDC by 3, and third step is pi by 3 angle from 2 pi by 3 to pi, which complete half cycle, and RMS magnitude will be VDC by 3, and it has both half cycles of symmetric segment of such step. So, the voltage rating of series active filter ESC is computed by taking the difference of the supply phase voltage and the required load sine voltage at the input of this. So, from this calculating the 3 segment, that we have a typically a sine wave segment, then the VDC by 3, then the sine wave segment 2 VDC by 3, and then again sine wave minus VDC by 3, and taking RMS it comes 71.15 volt, and the current rating of series active filter is your IS equal to IS 51.391 ampere, and the V rating of series active power filter will be 3 times voltage and current. So, putting the value of this, so it comes like a 10.969 kVA. So, coming to the 10th problem, a 3-phase active power filter connected in series with the AC mains and 3-phase and 3-branch passive shunt passive filter tuned for 5th, 7th and high pass is used for harmonious current and reactive power compensation, and 3-phase for 15 volt 50 Hz system to reduce the TAD of supply current and to improve the displacement factor unity. It has a load of 3-phase thyristor bridge converter operating at 30° angle, drawing a constant current of 150 ampere DC current. Calculate the A desired value of passive filter element, B line current, C V rating of series active filter. So, these are typical circuit that we have a supply voltage, we have a series active filter, we have a here the current fed the load thyristor converter feeding a constant current of 150 ampere, and we are using a passive shunt filter, and to improve the profile of passive shunt filter we are putting a series active filter which will force all the harmonious current required by the load into the passive filter, or you can call it passive filter will provide the harmonious current required by the load as well as reactive power, because at fundamental frequency this passive shunt passive filter behave as a capacitor. So, now what you have to generate to make adjustable solution, of course, since series active filter avoid the resonance, and it also generate the adjustable voltage across the passive filter or the point of common coupling, so that whatever the harmonious current are, they are pushed into the passive filter. So, after making the complete model of this system and putting the value of all data given the numerical problem, these are the simulated waveform, the supply voltage, supply current, we want unity power factor sinusoidal current there, and this is the typically the load current, which is the nature of thyristor converter constant output current, and the difference of these two is provided by shunt filter, and the series filter is responsible to with the small voltage, I mean to push all these current into the passive filter, all harmonious current and all harmonious current into passive filter along with the reactive current like. So, after this with the based on this waveform and all the data, it is a numerical part of it, given that a 3-phase AC line voltage of 415 volt RMS 50 Hz is feeding a load of 3-phase thyristor bridge converter operating at 30° phi angle, drawing a constant current of 150 ampere. A set of shunt connected AC tuned passive filter for this system is used to compensate reactive power, and 5th, 7th harmonics and high pass damped filter to compensate higher harmonic at the input main. And in this system, load current, harmonics and reactive power compensation are to be provided by shunt passive filter, and a series active filter is used to force all the harmonics current through this shunt passive filter. So, in 3-phase thyristor bridge converter, the current waveform load current is equal to C square wave on AC side with the amplitude of DC link current. So, IL will be root 3 by DC. So, it comes 122.47 ampere, and the RMS of fundamental of cos C square will be root 6 by pi into IDC. So, this comes 117.01 ampere, and active component from fundamental multiply cos theta 1, that is cos alpha, putting the value it comes 101.33 ampere, and the fundamental active power drawn by the load will be 3 VL into IL1. So, putting the value it comes 72.836 kilowatt, and the cos the fundamental reactive power of the load will be QL equal to 3 VL in IL1 sin L. So, putting the value, the reactive power required by the load comes 42.053 kVAR, and this have to be certainly provided by the passive shunt filter. So, the capacitor value have to be generated from that. So, passive shunt filter has a 9 branches, 3 for each phase and 9 for all 3 phases, and total reactive power of 42.053 kVAR required by thyristor converter it to be provided by the all 9 branches of passive shunt filter. So, considering that all branches of passive filter has equal capacitor, therefore, the value of this capacitor is equal to C equal to Q upon 9, 9 is for nylon element, putting the value it comes 259.21 microfarad, therefore, C5 C7 CH equal to 259.21, and therefore, the value of the inductor for 5th harmonic tune is calculated from this relation. So, it comes 1.565 millihenry, and the resistance of the inductor is calculated from quality factor X by Q5 taking quality factor of 20. So, we get the resistance 0.12 3 ohm, and the value of the inductor for 7th harmonic from this tune relation comes 0.798 millihenry, and the resistance for the 7th harmonic order is from again from x7 by q7. So, from qualify it comes 0.088 ohm, considering the q5 equal to 20, as it is in the range of 10 to 100 depending upon the design of inductor. The value of the inductor for a high pass time filter is for 11th harmonic. So, tuning for 11th harmonics we get the value of inductor 0.32337 millihenry, and the resistance in parallel of an inductor of the high pass time filter harmonics tuned is your XH upon QSH, taking a QH of 2. So, we get the resistance 0.558 ohm, taking Q factor of 2. So, it can be in the range of 0.5 to 5. And 3 phase thyristor rectifier with the quasi square wave AC mains current has a fundamental RMS current typically 117.01, and the 5th harmonic current to flow into 5th harmonic filter, that is I1 TS divided by 5. So, it is a 23.402 ampere, and 5th harmonic voltage at the across the passive filter will be I5 R5. So, putting the value it comes 2.875 volt, and 7th harmonic current of the load which have to flow into the filter, it is typically 16.72 ampere, and the voltage will your voltage of for 7th harmonic will be V7 equal to I7 R7. Putting the value it comes 1.48 volt, and all other harmonics load current to flow into the high pass damped filter, and so calculating that IS square minus fundamental square I7 square. So, we get the value of 21.92, and all other harmonic voltage at the load and across the passive filter, just putting the value it comes 12.24 volt, and all the harmonic voltage other than fundamental voltage at the load and across the passive filter we calculate from all harmonic, 5th harmonic, 7th harmonics and all head harmonics. So, putting the value this it comes 12.66 volt, and the series active filter must inject all these harmonic voltage to force all harmonics current into the passive filter. So, therefore, voltage rating of the series active filter series active filter will be 5th harmonic voltage 7th harmonic square plus all harmonic. So, it comes 12.66 volt, and the line current after the compensation at unity power factor, that IL1 cos theta 1, putting the value this, so it comes 11.1.33. So, therefore, current rating of series active filter will be the same as this current, and the V rating of series active filter will be 3 into VSH into ISH. So, putting the value it will be 3.8485 kVA, and the per unit of series active filter will be your V rating of series active filter divided by the load V rating. Putting the value it comes 4.37% of the load rating. Coming to the problem number 11, a 3-phase series active power filter connected in series with a 3-branch shunt passive filter, 5th, 7th and high pass filter is used for harmonic current and reactive power compensation in 3-phase 415 volt 50 Hz system to reduce the TAD of supply current and to improve the displacement factor to unity. It has a load of the 3-phase thyristor bridge converter operating at 30° firing angle, drawing a constant current of 50 ampere. Calculate A, the design value of the passive shunt filter component, B, line current, C, VA rating of series active filter, D, AC inductor value of active filter, and E, the DC link voltage of series active filter, and the F, the DC bus capacitor value of APF. Consider the switching frequency of 10 kHz and DC link voltage have to be controlled within 5% of the range, and ripple current of in the inductor 10%, and turns ratio of injection transformer is 1 to 10. So, this is typically the configuration which we discussed earlier, that we have a here current fed load, we have a passive filter to provide the reactive power, and all the harmonics we have to suck with the help of this series active filter. So, what series active filter is supposed to have to avoid the resonance and to generate a harmonic voltage of variable value, so that this passive filter sucks the current of that much harmonics as it is typically done by the load, and indirectly we can control this series active filter, so that the supply current are balanced sinusoidal and harmonic are forced into the passive filter. We can control indirect control manner. So, after making the model in MATLAB of the system and putting the value numerical value given in the problem, the whole system is simulated, and simulated waveform are here: supply voltage, supply current after the compensation, and this is the load current, and this is the passive shunt filter current, and this is the injected voltage of your series active filter, which is forcing the reactive, you can call it the all harmonics current into it, along with the of course the reactive power because of the capacitor. At fundamental frequency it behaves as a capacitive load. So, coming to numerical part of this, based on this waveform and data, given that a 3-phase AC line voltage of 415 volt RMS at 50 hertz is feeding load of 3-phase thyristor bridge converter operating at 30° phi angle and drawing the constant 50 ampere DC current. A 3-phase series active filter is connected in series with the shunt branch. 5th 7th harmonic high pass filter is used for harmonic current and reactive power compensation in 3-phase 415 volt 50 hertz system to reduce THD of supply current and to improve the displacement factor to unity. Consider the switching frequency of 10 kilohertz and DC bus voltage have to control 5% in the range of inductor current is 10%, turns ratio is 1 to 10. In this system, the load current, harmonics and reactive power compensation are to be provided by the shunt passive filter, and a series active filter is used in such all harmonics current through the shunt passive filter. So, in the 3-phase thyristor bridge converter, the waveform of load current, that is the input current, is Cauchy square wave with the amplitude of DC link current. So, you can call it RMS current, that will be √2 by 3 IDC. So, it comes 40.825 ampere, and moreover the RMS fundamental component of Cauchy square wave is typically from √6 by pi into IDC. So, it comes 38.985 ampere, and active power component of supply current will be IL1 cos theta 1, putting IL1 cos alpha, and putting the value, it comes 33.762 ampere. The total harmonics and reactive power component of the current IL square minus IL1 square under root of that, putting the value, it comes 22.953 ampere. So, fundamental reactive power of the load will be 3 VL into IL1 sin alpha, putting the value, it comes 14.011 kVR, and this has to be provided by passive filter capacitors like. So, the passive shunt filter have 9 branches, 3 of each phase and 9 for all 9 phases. So, total reactive power of 14.011 kVR required for the thyristor converter, which is to be provided by shunt passive filter of all 19 branches. So, considering that all branches of passive filter have equal capacitor, there the value of this capacitor is equal to QL upon 9 VL square omega. So, it comes 86.319 microfarad. So, it is C5 C7 equal to CH. So, it comes 86.31 microfarad. Therefore, the value of inductor for 5th harmonic tune from this tune relation comes by putting a C5 and omega 5, that is 4.695 millihenry, and the resistance of the inductor for 5th harmonic tune from calculated from X5 by Q5, taking Q of your 20. So, it comes 0.369 ohm. The value of the inductor for 7th harmonic comes L7, that is from this tune relation. So, it comes 2.395 millihenry, and the resistance of the 7th harmonic tune filter is X7 by Q7, putting the Q20. So, it comes by 0.263 ohm, and the value of the inductor for high pass filter for 11th harmonic tune. So, it comes inductor 0.97 millihenry, and the resistance in parallel of the inductor of high pass damped filter, the quality factor of 2.5 H upon this, it comes 1.341 ohm, and all the thyristor rectifier Cauchy square current have a fundamental current equal to √6 by IDC, that is 38.985, and the 5th harmonic current to flow into 5th harmonic is I1. So, that is 7.97, and the 5th harmonic voltage at the load point must be I5 into R5. So, putting the value, it comes 2.877 volt, and the 7th harmonic current to flow into 7th harmonic tune filter is typically this current divided by 7. So, it is 5.569, and the 7th harmonic voltage at the load and across the passive shunt filter is I7 R7. So, it comes putting the value 1.465, and all the harmonics load current to flow into high pass damped filter, that is IL1 square I fundamental square minus 577. So, putting the value, it comes 7.419, and all harmonic voltage at the end across the passive filter have to be putting the value of IH into RH. So, it comes 9.90949 volt, and the all harmonic voltage other than the fundamental voltage across the load end comes V5 square, V7 square, VH square, it is 10.46, and series active filter must inject all these harmonic voltage to force all harmonic currents into the passive filter. Therefore, the voltage rating of the series active filter is your VLH equal VSF equal to VLH, V5 square, V7 square and VH square, that comes 10.46 volt, and the line current after the compensation is at unity power factor, that is IS1 equal to I1 cos theta 1 IS1 cos alpha. So, putting the value, it comes 33.762 ampere, and the current rating of the series active filter will be the same as IL square minus the. So, it comes 22.93 ampere, and the V rating of series active filter with 3 VSH, putting the value this, it comes your 720.25 VA, that is the rating of series active filter. And the per unit of series active filter, that is the VA rating of series active, load VA rating, so it comes 2.45% of the load rating, and the AC inductor value of active filter from this turns ratio and from putting the value, it comes like a typically 15.504 millihenry, and the VSC side of AC injected voltage is your typically from turns ratio we get it comes 104.6 on inverter side, and the DC bus voltage for this generating this voltage, it comes 369.817, and the DC bus capacitor of APFT computed the change of sold, and so putting the value in this, so and minimum of 5% reduction, so it comes your 1080.291 microfarad. So coming to the 12th numerical problem, a 3-phase universal active power conditioner consisting of shunt and series active filter using 2 voltage source converter with the common DC bus capacitor is designed for a load of 415 volt 50 hertz thyristor converter, thyristor bridge with a constant DC current of 150 ampere, 60 degree firing angle of the thyristor. If there is any voltage fluctuation of 10% minus 20% in the supply system with the base value of 415 volt, calculate A the voltage rating of the shunt filter, current rating of shunt filter, VA rating of shunt filter, then the voltage rating of series filter, current rating of series filter, and the VA rating of series filter to provide the harmonics and reactive power compensation for unity power factor at AC means with a constant regulated sine wave voltage of 415 volt 50 hertz across the load by the series active filter. So, this is a typical system. We have a supply and we have a here the current fed load, and we have a universal active power filter. The series filter takes care of any sag and swell, so that the regulated voltage across the load, and typically the shunt filter takes care of harmonics and reactive power of the load, and of course, if there any circulating of power is required. So, after making the complete model of this system, I mean like MATLAB model of this system, I mean like and with the data given in the problem. So, the waveform are simulated. So, this is the supply voltage, supply current, the load voltage, and this is typically the load current, and this is the passive shunt filter current, which is difference of supply current and load current, and this is typically the series voltage injected for voltage sag and swell like. So, with these waveform and the problem, let us come to numerical part of this. Given that supply RMS phase voltage VSP equal to 415 by root 3 to 39.6 volt, frequency of 50 hertz, and non-linear load of 415 thyristor bridge current, constant current of 150 ampere at 60 degree phi angle of which thyristor. So, there is a voltage fluctuation of plus 10% minus 20% in supply with a base value of 415. So, let x be the voltage variation. So, VSP dash will be the PCC voltage under voltage variation. So, per unit voltage will be per phase voltage of load is 415 by root 3 to 39.6. So, in this system load current, harmonics and reactive power compensation are to be provided by shunt active filter of the universal active power conditioner, and voltage sag swell compensation provided by the series active filter. However, while compensating for voltage sag swell, an active power is circulated between series and shunt active filter as explained earlier. Under the maximum voltage sag, the maximum rating of the both VSC are realized and the various calculation are as follows. So, the supply voltage for maximum voltage sag is your Vs minus 1x, putting the x 0.2, so it comes 191.68 volt, and in 3-phase thyristor bridge converter, the waveform of load line current is quasi square wave with the amplitude of DC current. So, putting IL equal to root 2 by 3 by DC. So, put the value 122.47 ampere. Moreover, the RMS fundamental quasi square wave current, putting this relation root 6 by pi into IDC. So, it comes 116.95 ampere, and active power component of supply current is calculated IL1 cos theta 1, IL1 cos alpha, putting the value it comes 58.48 ampere, and the active power rating of the load is estimated 3 VLP IL1A, putting the value it comes 42,035.42 watt, and the supply current under voltage sag condition PL into 3 VSP. So, under voltage sag it is typically into this, so it comes 73.1 ampere, and the total harmonics and reactive power component of load current is estimated IL1 into IL1A square. So, putting the value it comes 107.61 ampere. So, voltage rating of shunt element of UV is equal to the AC load voltage, that is 239.6 volt per phase, and since it is connected across the load of 239.6 volt sine wave form, and line voltage rating of universal active filter will be again root 2 into 39/6, that is 415 volt. The current rating of shunt element of UPQC is computed as follows. The shunt active filter is to provide the load current harmonics and reactive power compensation, hence the required harmonic current and reactive power of the load it has to supply. Therefore, total harmonics and reactive power current of the shunt active filter is estimated as IL square, ISHR square, LAL square, IL1. Putting the value, it comes 107.51, and required fundamental voltage is lower as compared to the required load voltage. Hence, the shunt active filter absorbs the active power, and that active power is delivered back into the system via series active filter. The active power component of shunt active filter is estimated from IS dash minus ILV, and this is 14.62 ampere, and the overall current rating of shunt active filter will be ISHA square plus ISHR harmonic current square. So, putting the value, it comes 108.49 ampere. And the V rating of shunt active filter is 3 into voltage rating, current rating. Putting the value, it comes 77,989.45 volt ampere. And voltage rating of the series element of universal active power conditioner is estimated as there is a voltage fluctuation of plus 10%, minus 20% in the supply system with a base value of 239.6 volt. Therefore, the series active power filter must inject the difference of these maximum of these two voltages to provide the required voltage at the load end. So, the voltage rating of series active filter is your base voltage multiplied 20% sec, so it comes 47.92, and the current rating of the series active filter is the same as supply current, ISC equal to IS, that is 73.1 ampere. So, V rating of the series element will be equal to 3 VSC, and putting the value, it comes 10,508.85 VA. Coming to 13th problem, a 3-phase universal active power conditioner consisting of shunt and series active filter using 2 voltage source converter. The common DC bus capacitor is designed for feeding the critical load of 415 volt 50 hertz 3-phase and consisting of 3-phase diode rectifier, drawing AC current at 0.9 to displacement factor, and TAD of its current is 65%. It is drawing 40 kilowatt from the AC source, and crest factor is 2.5 of AC mains current. If there is a voltage fluctuations of plus 10% and minus 20% in the supply system with base value of 415 volt, calculate A, voltage rating of shunt element of universal active power filter, B, current rating of the shunt element of universal active power filter, C, the V rating of shunt active filter, and voltage rating of series active filter, current rating of series active filter, V rating of series active filter to provide harmonics and reactive power compensation for unity power factor at each main, and constant regulated sine wave of 415 volt at 50 hertz across the load by the series active filter. This is the typical circuit. We have a supply here, we have a load here which is voltage fed load. So, shunt filter is supposed to provide the harmonic compensation, and series filter is supposed to regulate the voltage across the load. So, after making complete model of this and putting the data from the typically from the given problem, the whole system is simulated, and these are the simulated waveform like supply voltage, then the supply current at unity power factor, and then this is the typically the load voltage, this is the load current, and this is typically the passive shunt filter current, and this is the voltage which are to be injected to regulate the typically the load voltage. So, coming to numerical part of this, given that supply voltage is VSP equal to 415 by root 3, that is per phase RMS voltage 239.6 volt, frequency of 50 hertz, feeding a critical load of 415 volt 50 hertz 3 phase, and consisting of 3-phase diode bridge rectifier drawing a current of AC current of 0.92 displacement factor, and TAD of AC current is 65%. It is drawing 40 kilowatt from AC source, and crest factor is 2.5 of AC mains current. So, there is a voltage fluctuation of plus 10% minus 20% in the supply system with base value of 415 volt, and load phase voltage is to be regulated to a nominal supply voltage of 239.6 volt. So, that is VLP equal to VSP 239.6, and let us be the per unit voltage variation, and VSB is the PCC voltage under voltage variation. So, in this case the load current harmonics and reactive power compensation are to be provided by shunt active filter, and the voltage sag sum provided by the series active filter. So, however, while combusting for sag swell, voltage sag swell, an active filter is circulated between the series and shunt filter, and under maximum voltage sag, the maximum rating of the both VSC are to be realized, and various rating calculation are here. So, the supply voltage under maximum voltage sag will be Vx into 1 minus x, putting the value, it comes 191.68 volt, and the active power component of load current is estimated PL upon 3, putting the value, it comes 55.648 and fundamental current of the load is estimated while cos theta 1. So, putting the value, it comes fundamental RMS current 60.487 and the load RMS current is calculated from the THD and fundamental current. So, it comes 72.142 ampere and the total harmonics and reactive component of current will be IL1 IL square. So, putting the value at 45.911 ampere and the supply current under the voltage sag is estimated PL upon the voltage here. So, active power divided by, so it says 69.56 ampere. The voltage rating of shunt element of universal active power filter is equal to the AC load voltage of 239.6, since it is connected across the load of 239.6 volt sine waveform, and current rating of shunt element of universal active power filter is computed as the shunt element of universal active power filter is to provide the load current harmonics and reactive power compensation. Hence, the required harmonic current and reactive power of the load it had to supply. Therefore, the total harmonics and reactive power component of current through shunt active filter is I load square minus I L, putting the value it comes 45.911 ampere and the supply fundamental voltage is lower as compared to the required load voltage. Hence, the shunt active filter absorbs the active power and that active power is delivered back to the system via series active filter. So, active power component of the shunt active filter is estimated as ISIL. So, that is 13.912 ampere and the overall current rating of shunt active filter is active component square plus harmonics and reactive component under root of that, putting the value it comes 47.973 ampere and the VA rating of shunt active filter is 3 into voltage rating current rating, putting a value, then it comes 34.483 kVA and the voltage rating of series element is computed as there is a voltage fluctuation of 10% and minus 20% in supply system with a base value of 239.6. So, therefore, series active filter must inject the difference between these two voltages to provide the required voltage at load end. The voltage rating of series active filter is 39.6 into the 0.2, it comes 47.92 volt and the current rating of the series active filter we have already calculated, that is IS equal to IS dash 69.56. So, V rating of series element will be 3 into VFS into ISC. So, putting the value it comes 10 kVA. Well, coming to the 14th numerical problem, a 3-phase VSI with Cauchy square AC line voltage of 440 volt RMS and 50 hertz is fitting for 15 volt line 50 hertz 3-phase thyristor bridge with the constant DC current of 50 ampere at 30 degree per angle of its thyristor. A 3-phase universal active power conditioner consisting of series and shunt active filter with a 2 VSC with a common DC phase capacitor is designed for this critical load. Calculate the voltage rating of shunt active filter, current rating of shunt active filter, VA rating of shunt active filter, voltage rating of series active filter and current rating of series element and VA rating of series active filter to provide the harmonics and reactive power compensation for unity power factor AC means by shunt element and constant regulated sine wave voltage of 15 volt 50 hertz across the load by series element of U. So, these are typically that we are getting the voltage from this Cauchy square wave and the load needs sine wave and this is the current fed the load thyristor converter. So, this shunt active filter is provide the reactive power and harmonics to the load and series filter is supposed to maintain the sinusoidal regulated voltage. So, after making the model of this system, complete model of this system and simulating this, we get the waveform with the data given in the problem like a supply voltage, the load source supply current, load voltage which are regulated sine wave and the load current, then shunt passive filter current, shunt active shunt current, active shunt filter current and active series voltage which are injected by here. So, after going through all these, so we can have a numerical portion of this. Given that a 3-phase voltage source inverter with Cauchy square wave AC line voltage with the VSL equal to 400 volt at 50 hertz feeding the critical load of 50 hertz thyristor converter and constant DC current 50 ampere at 30 degree fire angle. And in this system the load current harmonics and reactive power compensation is provided by shunt active filter and the voltage regulation and harmonic compensation to provide by series conditioner by of universal active power conditioner. However, the voltage regulation at active power filter is circulated between the series and shunt active filter. So, supply is the Cauchy square wave of line voltage of 440 RMS. The amplitude of Cauchy square wave, from this we can calculate the DC link voltage, that comes 538.89 and moreover the RMS fundamental component of Cauchy square wave is your SL1 equal to root 6 by pi, that is come 420.17 volt and the fundamental supply phase voltage will be VSL1 by root 3, the 0.58. However, the desired load voltage is 415 by root 3, that is 239.6 volt sine wave. So, this voltage is applied across the critical non-linear load of 450 Hz 3-phase thyristor converter with the DC current of 50 Hz at 30 degree phi angle thyristor. So, in 3-phase thyristor bridge converter, the waveform load current is quasi square wave with the DC current. So, we can calculate the RMS current, that comes root 2 by 3 into IDC. So, that is a 40.82 ampere, and moreover RMS fundamental quasi square wave current fundamental will be root 6 by pi into IDC. So, it comes 38.98 ampere, and active power component of supply current will be IL1 cos theta 1, IL1 cos alpha, that comes 33.7 ampere, 76 ampere, and the total harmonics and reactive component of load current IL1 square, IL square IL1 square under root of that. So, typically it comes 22.95 ampere. The active power consumed by the load will be 3 VLP into IL1, putting the value it comes 24,266.69 watt, and supply current is estimated as now 3 PL at unity power factor 3 into VSP1. So, it comes 33.34 ampere, and the voltage rating of the shunt active filter is equal to the load voltage 239.6. This is since it is connected across the load of 239.6 sine waveform, and the current rating of the shunt active filter is computed as follows. The shunt active filter of universal active power conditioner facilitated harmonics and reactive power compensation. Therefore, total harmonics and reactive power component of current through a shunt active filter is estimated as ISHR equal to IL square minus IL1 square under root of that. So, putting the value it comes 22.94, and the supply fundamental voltage is higher as compared to the required load voltage. Hence, the series active power filter absorb the active power, and that active power is delivered back to the system via shunt active filter. The active power filter current you can calculate IS minus L. So, it comes minus 0.42 ampere, because the voltage is more, so it has to feed power back to the via shunt filter. So, minus sign of active power component denotes that the shunt active filter supply active power absorbed by the series into the system, and the overall current rating of shunt active filter is active component square plus the reactive and non component square. So, it by calculating it comes 22.94 ampere, and the V rating of shunt active filter is your 3 into Vs into Is. So, putting the value it comes 16,489.27 volt ampere. The voltage rating of series active filter is to compute it as follows. The supply of quasi square wave line voltage results in a stepped phase voltage, and series filter inject the voltage which is equal to the difference between the supply voltage and voltage across the load terminal. The waveform of phase voltage at the input of series active filter is a step waveform, as a first step of pi by 3 angle from 0 to pi by 3 and magnitude of VDC by 3. Second step is from pi by 6 to 2 pi by 3 with a magnitude 2 VDC by 3, and the third step pi by 3 angle from 2 pi by 3 pi magnitude of VDC by 3, and it has a both half cycle of symmetric segment of such a step. The voltage rating of series active filter is computed by taking the difference of supply phase voltage and the required load voltage sine voltage at the input side. So, it will have a 3 segment 2 upon 3 pi in 180 degree by symmetry. So, this is VDC by 3 minus the supply voltage, again 2 VDC by 3 minus supply load voltage sinusoidal voltage, and then VDC by 3 then load sinusoidal supply voltage, and taking RMS it comes 75.46 volt, and the current rating of series active filter will be same as IS equal to IS 33.3, which we have calculated earlier ampere, and the V rating of the series active filter will be 3 VFS, and putting the value it comes 7,549 VA. Coming to the 15th problem in the 3-phase voltage source inverter with a step waveform of AC line voltage output of 415 volt 50 Hz quasi square wave 4 wire distribution system, 3 single phase load connected between phase and neutral, having a single phase 230 volt 50 Hz thyristor bridge converter drawing the 20 ampere constant DC current at 45 degree fire angle of its thyristor, a 3-phase universal active power conditioner consisting of 4 leg voltage source converter as a shunt active filter and 3 leg voltage source converter as series active filter using common DC bus capacitor is designed for this critical non-linear load. Calculate a voltage rating of shunt active element, current rating of shunt active filter, VA rating of shunt active filter, the voltage rating of series active filter, current rating of series active filter, VA rating of series active filter to provide harmonics and reactive power compensation for the unity power factor at AC mains and 0 neutral current by shunt element, and constant regulated sine wave voltage of the 415 volt at 50 Hz across the load by series element. This is the system that we have a quasi square wave, and by this inverter to the load, and we have 3 single phase load in 3-phase 4 wire system, and typically like shunt filter is providing the neutral current, harmonics and reactive power, and series filter is providing virtually the voltage regulation across the load as well as making the voltage sinusoidal, because this voltage is non-sinusoidal. So, after making the complete model of this system and simulating with the data given in the problem, the waveforms are here. The input voltage by Cauchy square wave, then the line current in phase with the sinusoidal balance current in phase with the voltage, then the load voltage which are regulated sine wave, and then this is the individual load current, one load current, then this is the typically the current by shunt active filter in one branch, and this is typically the series active filter voltage injected in, and this is the neutral current, you can call it a shunt active filter, and this is the load neutral current, which will be the sum of the 3 square wave kind. So, after going through this waveform with the data there, we have a numerical part of it, given that a 3 phase voltage source inverter with the step line voltage of 415 volt 50 hertz, Cauchy square wave of phase voltage fitting a single phase 230 volt 50 hertz thyristor bridge converter drawing 20 ampere at constant DC current of 45 degree DC current at 45 wire angle of thyristor for each 3 phases, and the supply is a step line voltage of 415 volt RMS. The amplitude of DC voltage from this SI is estimated √2 of that, it comes 586.899 volt, and the fundamental component of supply line voltage will be calculated from typically from this relation. So, it comes 93.296 volt, and the fundamental component of supply voltage comes typically 228.801 volt, and in 3 phase thyristor converter the AC line current is given of 20 ampere, and the fundamental component of, because it is a single phase, so it is a square wave, so that is the reason it came same as the DC of 20 ampere, and the fundamental active component is IL1 cos alpha, putting the value here, it comes 12.728 ampere, and total harmonics and reactive component will be IL square IL1 square, so putting the value it comes 15.427 ampere, and the active power consumed by the load will be 3 VL ILA, so it comes 8782.26 watt, and the supply current is calculated as from the power and the voltage across the fundamental voltage in the supply, so it comes 12.795 ampere, and the voltage rating of the shunt element of this equal to the at voltage of 230 volt, because it is a 4 wire system, and current rating of shunt element is calculated as shunt active filter of universal active power filter facilitate the harmonics and reactive power compensation. Therefore, the total harmonics and reactive power component of current through is estimated ILA minus LA square, so it comes 15.42 ampere, and active power component of shunt active filter is typically IS minus SL, so this comes 0.067 ampere. So, current rating of shunt active filter is your ISH square plus IS, putting the value it comes 15.427 ampere, and the RMS current of 4th lag inverter typically for the neutral current compensation is same as ISH and equal to is a 20 ampere, and the V rating of shunt element will be 3 branches plus the neutral, putting the value it comes 15.245 kVA, and the voltage rating of series active filter VFC is computed as follows. So, 3 phase VSI will be operated at 120 degree conduction mode to get the step waveform, and supply step waveform will be of S equal to RMS. So, step waveform will be of pi by 3 to pi by 3 angle 0 to pi by 3 and magnitude of VDC. Second step pi by 3 to 2 pi by 3 of 2 typically of your VD 2 VDC by 3, and third step typically of minus VDC, and it has a half wave symmetrical such will have amplitude of typically of this. Therefore, the supply step waveform is 586.89 results in a Cauchy square waveform of 3 phase voltage with amplitude of your 29 VD by 2 to 93.45 volt. So, however, the phase shift may be considered for phase voltage coincide with the sine waveform of 230 volt. The voltage rating of series active filter is calculated from these two segment. Putting this typically DC minus your AC sine wave and then AC only, because DC is not there. So, it comes 138.42 volt, and current rating of series conditioner is same as ISI equal to 12.79 as the current typically on the supply side 12.795 ampere, and the V rating of series VSC of series compensator 3 into VS into I. So, putting the value it comes 5.313 kVA. So, with this we conclude this hybrid filter. We would like to summarize here. A comprehensive study of hybrid filters is presented to provide the wide exposure on various issues of hybrid filter for power quality improvement. A classification of hybrid filter into 9 categories with many circuits in each category are expected to select an appropriate topology for the particular application. So, these hybrid filters are considered as a better alternative for power quality improvement due to reduced cost, simple design and control and high reliability compared to other option of power quality improvement. Since the circuit configuration of hybrid filter avoid the problem of involved in passive and active filter and therefore provide cost effective and better solution for harmonic elimination of the non-linear load. Any analytical study of various performance indices of hybrid filter for the compensation of sensitive non-linear load is made in detail with several numerical examples to study rating of power filters and how it is affected with the nature of various kind of non-linear load and supply conditions. Hybrid filter are observed one of the best treatable solution for mitigating the power quality problem due to the non-linear load and for reducing the pollution in AC main. And due to large number of circuits of hybrid filter, user can select the most appropriate topology with required features to suit the specific application. And of course, these are the references which we refer it in this, and well, thank you very much.